All right, welcome to The Explainer. Today we are diving into one of the most beautiful and, honestly, one of the most controversial ideas in all of physics. We're talking about string theory. So what is it? Why do physicists get so excited about it? And why does it drive some of them crazy? So let's just jump right in with a question that really gets to the core of this whole thing. We all learn in school that the universe is made of tiny little bits, right? Little particles like electrons and quarks. But what if that's just wrong? What if the foundation of everything is something completely different, something a lot more musical? Okay, so here's the big idea. Instead of tiny dots, string theory says that at the most fundamental level, everything is made of these minuscule, one-dimensional, vibrating strings of energy. We're not talking about guitar strings, obviously. Think of them as the absolute rock-bottom ingredients of everything that exists. And when we say small, it's almost impossible to even wrap your head around. I mean, look at this. If you blew up an atom to the size of our entire solar system, a single one of these strings would only be about as big as a tree leaf. That is just ridiculously tiny. So tiny, in fact, that seeing them directly is completely out of the question for us. Now, this is where it gets really cool. So how does one thing, a string, become all the different particles we see? Well, it's all about the vibration. If a string vibrates one way at one frequency, bam, we see an electron. If it vibrates a little differently, well, that's a quark. Vibrated another way, and you get a photon, a particle of light. It's incredible, right? It means every single thing in the universe, you, me, the stars, isn't made of different stuff. It's all made of the same stuff, just playing different notes in a grand cosmic symphony. But, and there's always a but in physics, isn't there? This beautiful, elegant idea, it comes with a price, a really, really strange price. For all the math to actually work out, the theory requires something about our universe that just seems impossible. And what is that price? 10 dimensions. Yep, you heard that right. The equations of string theory just fall apart. In the universe we think we live in, with 3 dimensions of space and 1 of time, for the math to work, for the theory to be consistent, the universe has to have 10 dimensions, 9 for space and 1 for time. Okay, so that leads to the obvious multi-billion-dollar question, right? If there are 6 other space dimensions, where are they? I mean, I can go forward, back, left, right, up, down. That's it. So where's the rest of reality? The best idea physicists have is that these extra dimensions are curled up. They're rolled up so incredibly tightly on a microscopic scale that we just can't see them. The analogy here is perfect. Think about an ant on a piece of paper. From way up here, that paper looks totally two-dimensional, right? It's just flat. But for the ant, it can experience the thickness of the paper. It's a whole other dimension that's invisible to us. That's what string theory suggests is happening everywhere, at every single point in space. Okay, so why bother? Why would physicists chase such a bizarre idea with all these hidden dimensions? Well, because the potential payoff is huge. We're talking about the holy grail of physics, a theory of everything. This is the one big problem that even Einstein couldn't crack. You see, right now, physics has a huge split personality. On one hand, you've got general relativity. It's Einstein's masterpiece, and it describes the big stuff, stars, galaxies, gravity, and it sees space-time as the smooth, stretchy fabric. But on the other hand, you've got quantum mechanics. This describes the tiny world of atoms and particles, and it's all chaotic and random. And here's the problem. They hate each other. They just don't work together. When you try to use both at the same time, like to figure out what's happening inside a black hole, the math just breaks. It spits out gibberish. And that is the grand promise of string theory. It's our best shot, our most promising attempt to finally unite these two warring theories. Because strings are fundamental. They can describe both the particle chaos of the quantum world and the smooth fabric of space-time that creates gravity. It could be the one single elegant framework that explains, well, everything. But remember that but from earlier? Well, here's an even bigger one. For all of its mathematical beauty, for all this incredible promise, string theory slams face first into a massive, real-world wall, a weakness that honestly has kept it from being fully accepted for decades. So what's the problem? We can't test it. To actually see a string or to prove it's there, we would need a particle accelerator with an insane amount of energy. We're talking 10 trillion tera-electron volts. To put that in perspective, that's not just a little more powerful than the Large Hadron Collider. It is a quadrillion times more powerful. A quadrillion. That's a 1 with 15 zeros. And as Professor Emil Amidov puts it, just plain as day. Is this technically possible? The answer is no. It's not a matter of money or time. We just can't. We don't have the technology, and we can't even imagine the technology that could do this. And that's a huge problem. How can you have a scientific theory if you can't test its most fundamental prediction? And look, the problems don't even stop there. Being untestable is bad enough, but there's more. The theory predicts a whole bunch of extra particles that we've never, ever seen. And maybe even worse, it seems to clash with what we know about the universe as a whole. The equations seem to describe a universe that's flat and not expanding, but we know for a fact that our universe is expanding, and that expansion is speeding up. So, where does that leave us? You've got this beautiful, powerful idea that seems to solve the biggest problem in physics, but it's also got all these massive issues. The scientific community is totally split on this. So, what's the final verdict? Well, there are two camps. You have the proponents who say, this is the closest we've ever gotten to a theory of everything. It's the only game in town. But then you have the skeptics. They call it a beautiful mirage, a stunning, complex cathedral of equations, but one built on a foundation that we can't test, that we can't touch. So is it the key to the universe, or is it just math? The honest answer is, nobody knows for sure. But maybe being right isn't the only thing that matters. The real value of string theory might not be in whether it's the final answer. Its value might be in the way it's forced us to think bigger, to imagine a universe that's just so much stranger and more beautiful than we ever thought. A universe built not on bits, but on music. And that leaves us with one last kind of haunting question, doesn't it? If the universe really is made of strings, if it's all just a symphony, then you have to wonder, who or what is playing the music?